Hey guys, how you doing? Welcome to Venus Neuron, your go-to source for medical school success. Now in this video, we're going to talk about chemical equilibrium and Le Chatelier's principle. So let's get started. What is chemical equilibrium? Many reactions are reversible and the forward and backward can occur at the same time. When the rate of forward reaction is equal to the rate of the backward reaction, we call that dynamic equilibrium. There is no net change in concentrations of the reactants and products. Now, what's the equilibrium constant? The state of equilibrium can be described by the equilibrium constant, shown with capital letter K. The absolute concentration can vary, but the ratio is constant at a given temperature. So, equilibrium constant and dynamic equilibrium is shown like this and calculated this way. Now, let's talk about law of mass action. It states that the rate of a chemical reaction, basically its change in concentration per unit time, generally increases when the concentrations of the reactants increase. Look at this diagram. The rate of the forward reaction is proportional to concentration of substance A and B. And rate of backward reaction, shown in red, is proportional to concentration of C and D, okay? But at some point of the time, from the purple that you can see, the rate of the forward and backward reaction is equal, and here we reach the equilibrium. Now, if when you calculate the equilibrium constant, it's less than 1, it means that the reactants are preferred. And if it's greater than 1, it means good job, the products are preferred. Now let's talk about Le Chatelier's principle. It states that if an external stress is applied to a system at equilibrium, the system adjusts itself in such a way that the stress is partially offset. Okay? Another way you can say it like this. If there is a change in equilibrium system due to change of concentration, temperature, or pressure, then the equilibrium will shift to the direction in order to compensate and re-establish the equilibrium. Now, what happens if we change the concentration? If the concentration of one reactant increases, then the rate of forward reaction increases and reaction shifts towards the products, like this. If the concentration of one product increases, then the reaction goes toward the reverse reaction. Now what happens if we change the temperature? If the temperature increases, it depends if we are dealing with an endothermic reaction or an exothermic reaction. Now before we keep going, let's talk about what are endo and exothermic reactions. They are two types of chemical reactions that differ in how they exchange energy, usually in the form of heat, with their surroundings. So, in an endothermic reaction, we absorb the heat from the surrounding. During these reactions, energy is taken in, usually in the form of heat, making the surrounding cooler. The reactants absorb energy to break bonds and transform into products, and the total energy of the products is higher than that of the reactants. So, the key characteristics are that heat is absorbed from the surrounding, the temperature of the surrounding decreases, and we have positive enthalpy change, which means that the reaction requires energy input. Now, before we move on, let me just tell you what is enthalpy. It's a thermodynamic property of a system that represents the total heat content or the total energy of the system, including both internal energy and the energy that is required to displace its environments, such as pressure volume work. In simple terms, it's the measure of the heat energy in a system at constant pressure. Okay? Now, moving back to endothermic reactions. What are some examples of that? We have photosynthesis, the process by which plants convert carbon dioxide and water into glucose and oxygen using sunlight as an energy source. Here, the energy is absorbed from sunlight to form glucose. Another example is dissolving ammonium nitrate in water. Ammonium nitrate absorbs heat when it dissolves, making the solution feel cooler. Another examples are melting of ice, evaporation of water, and cooking food, like frying and baking. Now let's talk about exothermic reactions. An exothermic reaction is a chemical reaction that releases heat into its surrounding. In these reactions, energy is released when the bonds are formed in the products, and the total energy of the product is lower than that of the reactants. The reactants release energy as they form products, and the energy release is typically in the form of heat or light. The key characteristics are that heat is released into the surrounding, the temperature of the surrounding increases, and we have negative enthalpy change. This means that the reaction releases energy. So when you see delta H negative, it's the reaction that releases energy. Okay? Examples for it are combustion of fuels. When a fuel like methane or CH4 burns in oxygen, it releases energy in the form of heat and light. Or respiration, the process by which cells convert glucose and oxygen into carbon dioxide, water, and energy. This process releases heat. Or except combustion like burning of wood, gasoline, and natural gases, we also have condensation of water vapor, for example, water droplets forming on a cold surface, or freezing of water, which releases heat when water turns to ice, or neutralization of acids and bases, for example, mixing hydrochloric acid with sodium hydroxide, which will be covered in the next video. Now let's move back to the Le Chatelier's principle and what happens if we change the temperature. If the temperature increases and we have endothermic reaction like here, the rate of the forward reaction increases. And if we have an exothermic reaction, the rate of the reverse reaction increases. So it goes to the left side. Okay, so here again. Now, if the temperature decreases, in an endothermic reaction, it shifts toward reactants. So rate of reverse reaction increases. And on an exothermic reaction, it shifts towards the products. So the rate of forward reaction increases. Now, what about the pressure change like in a gas state? If pressure increases, the reaction shifts towards the lower number of moles of gas. And if it decreases, the reaction shifts towards the higher number of moles of gas. Now, why does all of these happen? If a system in dynamic equilibrium is disturbed by changes in temperature, pressure, and concentration of its component, the system will tend to shift the equilibrium state so as to partially counteract the effect of the disturbance. The readjusted system establishes a new equilibrium. Okay, don't forget this part. Now, let me give you some bonus points. Some additional information. So, what happens if we add catalyst? Or why do we say that if we decrease the pressure, the reaction shifts towards a higher number of moles of gas? First, let's start with catalyst. It won't change anything, we just reach the equilibrium faster. But about pressure. When we have less pressure, so we need more molecules to collide. And since on the left side we have more molecules, so we go to the left side to have more collisions. Okay? That was why. Now you know it well. And that was all for this video. In the next video, we're going to cover acid bases and then talking about dissociation of weak acid and bases, and then types of salt reactions, and then buffer systems, and like buffer of physiological importance, and so on. Now, if you have any recommendations for new topics or if you have any questions, let me know in the comment section. Don't forget to like if this video helped you, and don't forget to subscribe for new videos, of course. And as I always say, stay curious, keep learning, and I'll see you in the next video.